So now we're going to talk about the other kind of algorithm, dynamic programming. And dynamic programming can be used for resource allocation. That's the kind of problem we have here. We're basically allocating how much money should we allocate to each of our roads and crossings. And what's powerful about dynamic programming is you can prove optimality and you can prove a global optimality. And the idea is you're going to break a problem into smaller subproblems. And so if you're smart about how you break your problem into smaller subproblems, you don't have to search the entire decision space. You can do a smart search and only look at the parts that are of most importance. And so this algorithm also helps us determine the best way to distribute our resources for each road and crossing. So I'm going to try to explain how you think about it. Each of these columns represent a road or crossing that I'm making a decision about. And then each of these circles here represents how much of my budget I might have left. So if I'm running my problem with $250,000, this circle here represents that I'm at the last crossing and I don't have any money left. And probably the only decision I have left to make there is to do nothing. While here I'm at my last crossing and I have $250,000 left. What do I want to do? And what I would probably choose to do is do full treatment. So again, similarly, this would say I'm at the first road, I have $250,000. What do I want to do? Versus I'm at the first road and I have no money. What should I do? So what dynamic programming does is it goes backwards. There's a number of different ways, but typically you'll start at your end condition. And so we can say if we had no money left and we were at our last crossing, our decision would be to do nothing. And if we had lots of money, our decision would be to do a full treatment. And at some point in time, we would change to intermediate treatment to no treatment, depending on how much money we have. Now we go to the next crossing, and again, we start with, assume I have no money. What would I do? Okay, this is how I'm working at subproblems. I'm not looking at the whole problem. I'm just going to say, I'm at this crossing. What are the different situations I could be in? I could have no money. And then if I would still have no money and I wouldn't do anything at the last crossing either. Versus if I had $250,000 left, I would do full treatment, but now I would have a little less money, but I'd still have enough money to do full treatment at the last crossing. Similarly, like here, I'd say, well, I don't have quite enough money to do full treatment, but I have enough to do some treatment, and then I'll have enough money left to do some treatment at the last crossing. So you basically go backwards through your decision space, and basically what's cool about this is no matter where you are, whichever road or crossing you're at, it tells you where to go and you have a path through the entire decision space. Dynamic programming has something called feedback control, which is pretty exciting. So what will happen is you'll say, well, really what I'm going to do is I'm going to start. Once you have your path through all of your decision space, you'll say, well, really, on this first road, I've got my entire budget. What should I do? And it says, well, let's do full treatment. And that would take you here. This is how much money you'd have left for the second to the last road. And this is what you should do here. And so on and so forth. And at some point in time, you would run out of money and you would come back up to zero. Now, this is just kind of a scenario. But what's cool is when you actually made this decision here, and what was the best thing to do, you actually took into account all of these different decisions. But you don't know that at the time you're making this mini decision. But there's a way of doing bookkeeping so that you are keeping track of that. And that's what's really smart about dynamic programming. So we do have some results, and with three main categories of results. One is comparing the dynamic programming to the uniform policy. The other is comparing the results from the genetic algorithm to the dynamic program, and then comparing those results for different budgets. So in talking with Marianne, one of the things we learned was, and I've talked with land managers at conferences as well, that sometimes all you can get a land manager say, and a regulator to agree upon is to do minimal treatment across the entire watershed. And so we wanted to compare what that would look like. And so we compared a dynamic programming policy. So we had minimal uniform treatment across the watershed, and then we told the dynamic programming problem that it had $250,000. And what you can see here is that if you do minimum uniform treatment across our watershed, it would cost $340,000 about. But the dynamic programming could actually would spend almost $100,000 less, but it would save 9,000, almost 10,000 more cubic yards, and with a much better cost-benefit ratio. And so what we were trying to say is we could use this tool to better inform road removal policy. So we ran the dynamic program and the genetic algorithm. We ran them with two different budgets, $250,000, $500,000. And if you remember, to treat the entire basin at full treatment, it would be $900,000. And you can see the costs, how dynamic programming and genetic algorithm spread it out. You can see that the genetic algorithm spent a little more money, but it's comparable in its savings sediment. And the cost benefit is pretty close. So remember, dynamic programming we can prove optimality. With the genetic algorithm, we can't. Similarly, for the $500,000, dynamic programming spent a little more than the budget. And again, you can see here, these solutions are very comparable. So the genetic algorithm did pretty well. What's interesting, though, is the genetic algorithm actual policies are a little bit more random than the dynamic program. So you can see there's a lot more variability in the genetic algorithm policy. So this is saying in the upper basin, do partial outslope everywhere. In the middle, do partial outslope everywhere. And in the lower part, do a little bit of partial outslope and some total outslope. But for the genetic algorithm, you can see that it's kind of doing a little bit of everything everywhere. That was for the crossings, for the roads. Here's for the crossings. Similarly, you see these policies look pretty similar, but you can see the dynamic programming is using more total excavation and then no treatment in the upper basin, but not so much no treatment in the middle and the lower. Well, here you can see the distribution along the genetic algorithm. So what we were able to show that optimization policies were more cost effective than a uniform policy, which was those were the policies we were more likely to see used. But the dynamic program and the genetic algorithm actually had very similar treatment policies, particularly with the amount of sediment saved versus the amount of money spent. But we did see that the genetic algorithm policies had more variability. And what was pretty cool and key about this was it was a watershed approach to thinking about how to remove sediment input as opposed to a road approach. And so that was a fun thing to point out at the time. So I've had students continue this work past this particular presentation. And so we had someone work past this. Chris Baker looked at stochastic dynamic programming and did some Monte Carlo analysis with that. We also did some experiments looking at critical habitat weighting factors. We were able to show pretty different policies based on that. And the really interesting question that Marianne's pretty interested in is, every season that you don't treat the watershed is a season that you're risking it being the big one, where we get the 1 in 100 year, the 1 in 500 year storm that will really make the sediment move. And so looking at, for those of you who are taking probability, it's looking at that trade-off between the risk of treating less effectively right now, but treating more, versus treating more effectively now, but treating less and risking having that exposed sediment for later. So with that, I'm hoping you'll ask some questions. You can pose them on Moodle with your weekly comprehension assessment, or you could pose them on Piazza. Thanks a lot.